Hi, I'm Ori. I work for App Dynamics. App Dynamics is an application monitoring and observability space. We do a full stack observability. I'll be sharing more details about App Dynamics in one of the slide I have. I manage both metrics and traces in App Dynamics data platform. Binder, go ahead, give a quick intro, and then we'll start with the slides.
Sure. Hi, well, my name is Birender. I'm a software engineer in the academics in the data analytics. I have been working with Druid systems for about a year and a half to 2 years now. Thank you.
Okay, let's get started. We'll quickly cover observability, and the agenda of it today is we'll give a brief overview about what observability means and some concepts of open telemetry, and then we'll get into the other aspects of the presentation around data modeling, metrics, attributes, percentiles, and aggregations. App Dynamics. App Dynamics is a 13-year-old company. We started with traditional APM-based monitoring, and now we do a full stack observability. In full stack observability, we do end-to-end of IT stack from business, users, applications, infrastructure, network, and security. We not only provide a visibility on the end-to-end IT stack, but we also help in enabling and setting up automate actions where you can take corrective actions to fix performance problems in any of the layer you would observe issues with. In general, observability is a very generic term. It started with control theory. And I'm not going to give you a mathematical or a control theory definition here. But in general, from perspective, observability gives us an ability to understand the internal state of the system and also observe the health of the system through a telemetry data we collect. Journey of the observability begins with collecting telemetry data, and primarily metrics, logs, and traces are telemetry data which you would collect for the service or a software you're monitoring. Pillars of observability. Again, key pillars of the observability are metrics, traces, and logs. And some others may say that the context or a few other things are also relevant for observability and they may as pillars. But I would say metrics, traces, and logs are the key components, and every observable system we build should have each of these key components in it. The need for observability. Observability, traditionally, we used to monitor monoliths in an application and also a three-tiered architecture-based systems, where most of the observability was done through, or monitoring was done through metrics, capturing the data from the entities where we observe the metrics, and then set up some alerts or take some predictive actions around that. Observability has changed as we started building modern systems, and modern systems are complex, they are distributed. Now, the traditional way of monitoring in terms of metrics would not work here. The way some of the use cases are still relevant, people do need to collect the data, view it for the historical purpose, set up alerts on them. But the system as such has changed, and the entities and the layers have changed. So with observability, when it comes to health, you would be not just capability where you could set up some pre-configured alerts, but you should also have the ability to know the health of the system. Where, let's say you are working on a Kafka-based system, and there is a network in one of your topic. Alerting on the topic lag in itself is not the actual root cause. It could be it's one of the network socket or a switch has an issue, and the layer could be on the network layer we need to identify. How quickly you're going to identify that issue is the part of the observability system. And when it comes to correlation, like the systems are complex, they are distributed, and even though you may work in an application layer where you are interested in knowing about your service, like errors per minute or calls per minute, that in itself gives you only some context. It doesn't give you a full picture. Having a correlation helps. It helps you to associate with various entities. It helps you to gather the data from various domains and have a meaningful running your queries. Not everything pre-computed or aggregated. You will be able to, like during the read time, during an interactive way, you will be able to get deep and rich insights from the system. Now, the reason why people use observability is to debug or troubleshoot. You would be like, it depends upon the persona who is like looking at the system. Primarily, if it is like dev or DevOps, they would be interested in knowing about the issues they're having with the system. The same thing applies with similar to health for the debug too, where the systems are complex, and when it comes to troubleshooting or debug, the problem may not rely on the layer or the code which we have written. How would the observability system give us a view where we could like get a deep or like able to pinpoint the root cause in a minimal time? And same thing with the failures and applications, where the operation failures could be like related to the environment where your applications are deployed. It could be in a Kubernetes cluster, or it could be in some form of like public cloud where your applications are deployed. And application failures, when it comes to observability, you would be adding observability for monitoring or gathering this telemetry data at a leaf entities. Like if it's a logs, you would be gathering at a service or a container where the application is running. Similarly with metrics, it could be some collectors which are deployed with that application, or it could be some form of exporters through which the data is gathered. Now, querying only on leaf level entities, like if it's a container or a pod, will not give you a meaningful information. Like how do you are able to associate that with your telemetry data, and ability to pinpoint the problem becomes a crucial part of the observability. And the next case of exploratory, similar lines, where you are like not like you will not be able to store all the context, all the data, and also able to like grep to the log files and find how your system is working. It need not be an a issue or an error or a failure. It could also be you want to gain about your system, like how your load is distributed across your pods, how you are efficiently using your resources. It could mean anything. So the of observability has changed with the modern and distributed systems. I'll be like covering on some of the open telemetry aspects, where open telemetry is next popular project after Kubernetes and CNC, Cloud Native Compute Foundation. In OpenTelemetry project, it has provides certain protocols and specifications, and also has some client libraries, collectors, all related to the instrumentation of telemetry data. It's the instrumentation will be able to like you'll be able to gather like metrics, logs, and traces, and also it is open source and vendor neutral. OpenTelemetry is not a backend. It's a project. It's an instrumentation. It defines standards, and it has some collector libraries where you can gather data from your systems. Where you need not like build a vendor specific libraries associated with your system. It's like a common open source, and it's also the popular languages. Open telemetry data is collected by backend systems, Agile or a Prometheus, or also any kind of like a commercial backends. I'll touch a few concepts about like metric modeling and context, primarily from the open telemetry side. And we'll cover more details related to metrics and why, like the observability or challenges we have with metrics. So setting up this, some of the context about metrics would help us in the discussion there. So in open telemetry world, when we look at a system, the data is gathered in terms of measurements or events. Like if you have something like yeah, before I go into the the definition of the flow of the metric data, one key note which I need to explain is metrics are time series data, and measurements are like events which you observe about a system. If you have a metric like CPU usage, now CPU usage, you could gather it at like at a nanosecond level or a microsecond level or a millisecond level. Now you will not be able to, or like willing to store that data or query the data at the granularity. You would be aggregating the data based on time, and then you would be rolling up that as a metric and observe it. So raw measurements are the granularity with which you're observing the one way of aggregating the metrics I said in terms of time. That other would could be also be relevant to the domain. Like if you have a bunch of network cards, you are not really keen on looking at the values at an individual network card, but you want to actually look at the values combined together of all the network cards. So OpenTelemetry collectors, they treat the raw values as measurements, and then the instruments. Primarily, there are like three types of instruments here. Some are like called as counters, where counters are used to sum the values. If you have an example of a metric like calls per minute, you would be like doing a sum for it. And there are other types of metric instruments like observers, where observers are like you want to know a point of time value, CPU usage. Maybe you're not really interested in looking at the uh, total number of values you observed. You just want to pick the current value and send it. Or it could also be like a temperature or a sensor. Those values are like aggregated based on the type of metric instrumented. The values are computed into a metric event, which is time series in nature. Also, another concept of aggregation temporality here, where the metric event, when we compute, we also add some more context, like whether is it a cumulative value which I observed for the current event time, is it a delta? Like cumulative is like the total time from the period where the service was running, or is it a delta where it represents the time interval for which the metric event was computed? OpenTelemetry has three types of metric types: sum, gauge, and I'll sort of like covered it in the explanation I gave related to the measurements and metric events. Now, metrics are like raw values. They give you some context. They themselves will not like give you a more deep context to gain insights on. When you associate a metric with a context, like the environment it belongs to, the version of the service it is running, the type of the namespace where the service is deployed, that's a context which you want to associate with metric point. And it gives you like a rich analytical way to query the metric data. Now, the context as such can be associated with all forms of telemetry data, metrics, logs, or traces. A few more basics about metrics. OpenTelemetry provides metric API and SDK, which allows you to like compute the reprocess the raw measurements and then extract a metric event out of it. The context is called as resource, and in context you have something called as labels, tags, which are like a key value pairs you're associating with. In case of metrics, you're associating that with metric event. Now, aggregation I did explain in terms of the different like the counters, observers, and in terms of how the raw measurements are combined into a metric event. Resource. as I said, like metric represents a value, and resource is the context which can be associated with all the metric values. So it's like service name, service instance, environment, or service version. A metric event from OpenTelemetry will include the instrument, list of labels, the measurement applied, and the time for which the metric has been reported. Few examples of metrics across the stack, business metrics could relate to the user journeys. System metrics relate to the infrastructure which you're monitoring. Infra metrics could be like a cloud and the environment which you're looking at. I have covered the slide and the example in the past slides too. Now, when it comes to metrics, side we do sampling because it's not like if you store the raw events, it's not possible for us to represent it as in a time series fashion. Aggregations, like it happens during the collection time, and also we do aggregations to correlate the data. You may be observing the values at a leaf level entities, and you may have some form of like a hierarchy or a topology. The data can be aggregated based on the schema and rolled up. Similarly, metrics are like we need like for a historical purpose, we need to retain it for a longer time period. And a time-based retention is some form of like downsampling the raw metrics we gather. Metrics on the query side, they can be surfaced in some dashboards, some graphs, and plotted on it. It could be like some browsers can be built and queried on it. So any form of like interactive visualization it can be built for getting a deep insights on observability. Full stack analytics, it's like the problem may not rely in the same layer where you're observing. So if you're doing like looking at an application metrics, you still may want to up some context from the cloud or some context from the environment where it is deployed. Other common things we do with metrics is like we set up alerts on them so that we can closely look at our system, and if it reaches certain thresholds, you could take some corrective actions on them. Similarly, anomaly detection helps you to find outliers. So alerting is kind of like a most a rule-based system, and anomaly detection is more like you will have some ML algorithms to identify how any outliers which will be relevant for you. Ad hoc queries are like other exploratory things. When we build a metrics platform, we need to basically connect the dots across the entire IT stack. We need to provide a full stack observability with a business lens, which is like if our customer is like a Yelp user, we need to provide the journey of the user, like how the user has been engaging with across the systems in some form of way. It could also be applied to the traces or logs too. And the other aspects are like one of the challenges we see with metrics is the data gets gathered at it could be like millions and or billions in terms of how we process in total number of metrics. So availability of a metric system is highly crucial. On the query side, it depends on like the volume of the queries and the concurrency of queries we need to support. Metrics are like long-term, we need to retain for longer time for historical purposes, and that introduces the scale challenges we would have in building a metric system. Some of the aspects of like managing data store in metrics, we find that there are a lot of dimensions we need to add, and how would we like scale in terms of indexing for those dimensions. Cardinality is something you would hear when if you have worked on like a Prometheus kind of system where adding a large number of labels will create a humongous number of time series, and that introduces the problems of cardinality. Similarly, with low cardinality, you may run into some problems with high volume aggregates you would do. As the cardinality is low, there will be like a larger number of time series which would be selected for that, and you may are running some aggregate operations on them. Locality is a common problem which you would see in any distributed massively scalable systems. How do you organize your data in your shards or partitions? So if you apply some kind of context, you may apply for certain types of queries, but you need to look at how the locality can be managed without in a generic sense. Big fat queries, when you have data volumes at like a petabyte scale, you need to look at why, if you have some interactive visualizations to support, then you need to ensure that query latencies are sub-second. So the number of time series we fetch and the number of time series we aggregate in the read path becomes crucial for us. And one another aspect of the system is the cost aspect. With scale, how do we keep our cost in balance and then also manage our query times? With this, I'll hand over to Birinder, and he will walk you through more details on the some set of systems features we have been working on. Birinder, should I stop sharing?
Yes, please.
Go ahead, Birinder.
What I want to start here with, based on what I was going to describe about in the context of open telemetry, the data model, like the context, the resources, and the metrics. That how do we get that model and model into the systems that we use in AppDynamics, and then going forward, explore around the problems that come around around the number of dimensions, the attributes, and for the total number of metrics that you have to query, relationship between these different entity types, and then talk about those problems in detail. Okay, so starting from the open telemetry model, what we get here is, but first of all, we get the entity types. Entity type is an example of an entity type is anything on which you are getting measurements from, and an entity type might be an EC2 machine, an Azure VM, or a whole application, or a single user running single instance of an app running on a user's cell phone. Each one of them is a type of entity, but then these are the abstract types, like they are the Java classes, but like the actual objects, the instances of these types, they are called entities. Now, the entity types themselves, first of all, they are related with other entity types. For example, an application might have hundreds of services. A service might be running on thousands of pods. So these are the relationships that they have, and these relationships are hierarchical as well as non-hierarchical. And then there can also be subtypes between these relationships. For example, let's say we have a service running both on the an EC2 instance and some part on an Azure VM instance. So the parent type is simply just a machine, an abstract machine, but the child types are EC2 and VM, and then we might actually want to compare the performance of your services based on the machine type, whether it's EC2 or Azure. So there are subtype relationships, and there are metrics which get inherited across these subtypes. And then then finally these types also have attributes assigned to it. For example, an attribute is like, let's say an AWS region is an attribute, and you want to compare the performance of your services running in US versus Asia Pacific region. So this is an example of attribute, and then this attribute also gets passed from the EC2 entity up to the service or the application layer. This will become a little more clear in the next slide. Then on the last thing which we want to talk about is domains. So what we are measuring, when we are measuring metrics, we want to measure it even for the same entity. We want to measure metrics from different perspectives. We want to measure it, get the cloud metrics like from CloudWatch for that entity. We want to look at the infrastructure metrics like CPM, or network metrics like network calls in. So all these ways, these are the different domains that we can divide these things into an entity type into. I will have in the next slide, I will provide an example of this to make it more clear. So now, similarly to entity types, we have metric types, which are like a CPU metric is one CPU uses metric is one metric type, but when it is attached to a particular instance of an entity, then it becomes an actual metric. Now, in a metric, there are few salient features. One is that the data type that we use, whether it is a log or a double or a float, and then there's a granularity. Like some people might be measuring this metric at a sub-minute granularity, either at a minute, and then other CloudBurst metrics might be at a 5-minute granularity. So these are a set of differences. And then the metrics themselves, the way the metrics they are derived is also different. Some metrics they are reported directly by the system, by the application. And other metrics can be generated from logs or spans, etc. For example, be interested in how many errors did I see in the past 1 hour of running this application on a machine of this type. So we did this is what we call a derived metric. It is like, for example, derived from logs. So this is one more way the metrics are related. And of course, we got attributes, etc., at an entity or metric level itself. Like we may, for an example of it might be, we have a service owner for a particular service, and or a department which uses the particular service, and we want to use that use the number of machines that we are using to assign some budget or bill to them. So it's a attribute at a entity level. So this is the attributes and all, they can be at the type level as well, and they can be at the entity level itself. So moving on, the next is data. This is an example of a data model. Let's start with the domains first. Now you see these different colors. They signify domains. Like EC2 and Azure VM, they are both in the cloud domain, and then EC2, both of them, let's say, example, can run multiple Kubernetes pods. A pod can have multiple containers, which both these two will be monitored by something called infra domain, because they are the infrastructure things. And then we have the application domain, which is like the service instance. A Docker container might run multiple service instances, usually only 1 or 2, but it still can run, theoretically it can run more. And then service instance can be a part of one service, but one service can have multiple such instances, and then one application might have multiple services running in. So these are the three things in the domain that, and you can see how the attribute propagation happens. Like this AWS region attribute, we might want to propagate it right up to the service level, so that we can find out that how is my service running in region Asia Pacific versus US West 2. Similarly, look at the metrics also. Like let's say the application monitoring domain, we got metrics: calls per minute, average response time, errors per minute. We might also want to propagate these metrics up to service or the app level, so that we can see for the complete application how many errors are we getting, and obviously then also slice and dice them by the AWS region or an owner of a service, which service is throwing me more errors in my application. So this just gives an example of the complexity of the system in terms of hierarchical relationships as well as non-hierarchical relationships. For example, there is no relationship between them, but they can both be a subtype of a, I have not drawn something here, of a abstract monitoring entity type called machine. Now let's go through some of the challenges that we faced with the metrics. So as you can see in the model, we can have thousands of different entity types, and the number of metrics that can be associated for an entity type, they can be variable. At the minimum, we estimated it will be at least like 5, and can be even 100 or even more for something like a when we start monitoring the network related metrics, then it can even go up very differently, and they will all be named differently. Like the metrics for the name for metrics for one entity type will be different from the metrics of another entity type. And then the metrics themselves, the way people will want to query metrics, they can be expressions in them. People might want to see the CPU uses when your calls are very high, or the memory uses when your response time is slow. So we are allowing people to create these metric expressions and then query them, and the expressions, they can work on metrics of a single entity type, but they can also be used on the metrics across different entity types. So a few approaches that we consider, that in Druid, how should we store the metrics and dimension, the metrics and dimensions together. So by dimensions, we had some fixed set of dimensions like the entity type name, or tenant ID, or the and then all the attributes. And then for the metrics, we had those 5 to 100 number of metrics per entity type. So the first approach we considered was that, okay, store all the metrics in a for an entity type for a single row. But that had some problems. First of all, it made the table really wide, and the table itself was contained very sparsely populated metric columns, so it did not really scale well. After that, because consider the number of metric names that we can have. We have 1,000 entity types with 100 different metrics names. We have 10,000 different metric columns, so the table will become really wide. It won't scale. And then what we thought, okay, let's try to fix the metric column name. Let's call them A, B, C, D, E, and create a mapping between our metric names to these fixed column names A, B, C, D, E. It seemed to work well for fine, but did not cover all of our cases. One thing was it was very inflexible if we were to change our data model, because then whatever we are writing into that A, B, C, D column, if we have to change the definition of it, then we won't be able to do that. Second, number two was that it did not allow us to query the same metric across multiple entity types, because they are named the same across 2 different columns, but the entity type dimension is different. We cannot really use metric expressions over them at all. Then the third thing we considered was, and it was just a small consideration, that maybe we want to split the data source by entity type, because 95% of our queries, they were constrained on single entity types. But then it really won't scale either, because we'll have at least thousands of different data sources, and it will be a nightmare when we will try to maintain this. So what we eventually ended up doing was we decided that we'll put the metric name itself in the dimension, and then use only a single metric per row. So the only problem with that was that there will be duplication of dimension data across multiple rows, the same record type. But so the dimensions we will keep on repeating in the subsequent rows again and again. But then we used a couple of steps which helped us to optimize the compression. First thing we did was we used secondary partitioning on record type, so that one segment file contains most of the records belonging to a single entity type. So that solved us for the data that we'll store in historicals. And we were also going to query data, some data from the indexers. So for that, we decided that and most of our data was real-time ingestion, that based on the record type or an entity type, we will submit the record to appropriate Kafka partition, so that they did even within the indexer, the segment file that are easily created and that are present before compaction happens, they end up having entity types belonging to a few set of those 1,000 odd types, instead of it uniquely distributed. And obviously we had to use some logic for making sure that there is efficient load balancing happening, because some entity types might have a lot of metric data, some might not have a lot of metric data. So now, since we did our segment file contained a constrained number of entity types, so our query performance actually also improved when we switched to this model. So as you see that one entity type can have tens of attributes, and some of them will be very high cardinality. For example, think of an entity type called a particular app that you're monitoring, and then you are also always ingesting the user ID as an attribute. So a user ID for an application can be millions, so it can be very high cardinality, or it can be something which is like really low cardinality, like an AWS region, which has only like 20 values across the whole world. And then when we were going to query them, the way we were going to query them, we were going to filter or group across multiple of these attributes. And also because of the way, if you will remember the way we were transitioning the AWS region from EC2 up to service and application, the same attribute name can be shared across multiple different entity types, and we might want to query them together. So one of the ideas was that, okay, the problem that we had to solve was, okay, what should be the name of the dimension that we should give to these attributes. The first idea obviously was, okay, use the attribute name itself as a dimension name, but that will lead to tens of thousands of dimensions, which is for each segment file, we can have large memory maps and metadata in each of the segments files, so that won't scale. So what we decided to do is that we decided to use multi-value dimensions. We'll store the attribute in attributes in multi-value dimension columns. We'll store the key value attribute, like each attribute is a pair of key and values. We'll store it as a single key value string, key colon value. What it helped was it helped with data locality, because all the different because the key and value themselves, they will be stored in the same column, so we don't need to filter or group across multiple dimensions. If only so that helped with this. But then we had also some use cases where people would just want to query for the existence of a key. So we stored one more extra column just to store the attribute keys as a multi-value dimension. So since for a segment file, the overall cardinality did not change because of it. So ultimately, it did not impact the size of our bitmap, but it definitely impacted the size of the memory maps and all that we had to create. Some specifics about what we did was, for the multi-value handling parameter, we used this a sorted array. For the second, if you were to refer to internals of a segment file, there is a list of column values, so it provided us better compression performance over that. And for the numbers that we came up with was that about 10 tags per row, we are able to tune the size to 372 bytes per row based on the cardinality estimates that we had for the data that we are going to have. For segment size with million rows will go to 372 MB, which seemed pretty ideal for the numbers that we were targeting. And then we're querying. Then we wanted to query based on a specific key or value only, because multi-value dimension, if you don't, it will give you, if it has tens of different keys, then different values in a multi-value dimension column, then it will give you 10 different copies of that row. So we decided to use filter dimension spec, which scaled well. Our query performance is still a little bit high, but we have not spent enough time, to be honest, tuning it. But we are going to start tuning it even more. Like our P99 still hovers around 2 seconds. We are facing some high CPU uses and high number of minor GCs, so we need to tune a bit more on this one. So the last thing that I want to discuss is the percentile metrics. We have some, we are ingesting percentile metrics in our systems also. A size of a uncompressed percentile matrix in JVM is around 1.26 KB. What we are doing is that percentile matrix, since the size of the matrix is much higher compared to the actual matrix, which is usually a log or a double, we are using a separate data set for percentile matrix. Then we are using for the actual percentile matrix implementation, we are using TJS instead of the default HRD histogram, because uncompressed size for TJS is around 5x smaller than the HRD histogram. Although compressed sizes for HRD is bigger, but compressed was not giving us the latency that we wanted, so we went with we wanted to go with the uncompressed TJS. Accuracy is still lower than HRD, but we are still fine with it's still within our bounds. Add time for min data during merging and merge time for hourly data was a little higher, but we are still within our bounds. We decided to go with TJS based on the requirements. some numbers on performance. When we are doing perf test, one thing we noticed was that we'll hit hardware limits for reading percentile data. So we switched to using i3.xlarge historicals because they could. We were hitting discrete issues, so they had SSD storage, so we could scale up to 10 GB per second discrete. And so max GC time, it lowered it. When we were hitting high GC time, it lowered us to, based on because the CPU and RAM, it lowered us the GC time for us to 3 seconds. So we were able to hit a P98 of 800 milliseconds. And then since we're also doing secondary partitioning based on entity type, just like we're doing for the normal metrics. So that also helped us to achieve the query performance that we wanted. So the last part of this presentation is aggregation. So we wanted to do aggregation on two models. One was across the topology that we created, which we call the space aggregation. So for example, we want to roll up metrics from a service instance to a service, aggregation of calls per minute service to an app. And so our default UI pages we will load application level at the higher entity type level. So we wanted to avoid querying a lot of data. So build up a small Kafka streaming service to aggregate based on the topology. And then obviously we had to do some time-related aggregation where we were to make some choices between performance and accuracy. So which were done at a few places also. The ingestion agents themselves, the OpenTelemetry agents, they will do some to start with. They won't provide some granularity. They will do do an aggregation from sub-minute to a minute granularity. In the future, we are keeping the option open to also support sub-minute granularity. Then what we are doing was that when within our data store, when we are reading data from 8 days for minute data for 8 days and storing it in a different data source with an hourly granularity, because some of the queries which don't demand a lot of accuracy, for example, for calculating baselines and all those things, we were okay with querying data at a higher granularity. And then we are using separate storage size for the data sources because the daily data is going to get queried more oftenly and more aggressively than hourly data. So we are using separate storage size for these. And the last part is the aggregation that we do for the on the query side of things. These are obviously performed in Druid. So one thing is regarding the aggregation that we have to do on the attribute keys and values. Those ones we are doing in Druid at query time because the combinations of those keys and values can be infinite. So the pre-aggregating them doesn't make any sense. Another thing is that sometimes if the query is for a very large time, on the UI screen, you cannot, if your data is on a minutely granularity, you cannot show so many data points. There is no point in showing so many data points for, let's say, a week. So the space on the screen is limited. So then we are also rolling up from the minutely to 10 or 20 minutely or other in granularity based on the size of the screen, and that's happening dynamically within Druid itself. Going to the next one, questions. So I see there are no questions right now in the Q&A chat.
Thanks a lot, guys, for the great session, by the way. My name is Joe from Imply. So if anyone has any questions, please put it in the chat. We'll make sure we get to them.
Yes, we'll work with Imply and put the slides in the comment deck, and we'll share it.
Looks like we have one question from Ashok on how is the data quality checked.
Yeah, Druid had been pretty clear in terms of the requirements that we wanted from it, and perf wise, we have also been able to scale it up to decent numbers. but we are still trying to add more and more use cases to it. So we'll see how it goes.
Yeah. So one of the aspect of observability system is there is no one single parameter on which can be tuned. There are actually quite a number of them. With data model, it is complex. The cardinality comes into the place, and the volume increases. At the same time, we also have limitations in terms of the query latencies we need to support. So with all of this, Druid actually gives us a lot of flexibility to tune around things, and it helps us to deconstruct the components. Like if you have like a more heavy indexing needs, we could allocate more resources for the indexing side and do that. If the tiered storage gives us a flexibility to play around with the retention periods, and also gives a very deep insights about what happens within the system. So far, like we are able to accommodate all the requirements we have from the product. Next question, did you have any issues with joining data across different layers? Um, I'm not sure if you're when you say different layers, yeah, we are sort of like not doing joins. We are not partitioning data based on the domain or the type of data. And primarily the reason for this is our query latencies needs to be sub-second, and joins are still they fall in the bucket of 5 seconds to 30 seconds. So the complexity of joins actually comes in with our side. How do we model the data in such a way that not have a requirement for joins, and we can still store petabytes of give you sub-second query latencies? Next question from Tanman. How do you handle data retention, compression, compaction, aggregations? So data retention is implicitly handled by Druid. You could set it across a data source, and base like Druid is loosely coupled. So you could allocate resources based on your query volume, and you can we sort of manage it through data sources to support a longer retention period by downsampling the data. Other things like compression and compactions. Compression, we haven't changed in terms of how the data is apart from some custom data we store. Compactions, we have tuned compactions for Druid. Primarily, the new features added to Druid, we are heavily relying on secondary partitioning through our compaction jobs. And aggregations, we do it across the stack. We do it pre-ingestion of the Druid data to Druid, and also once the data is stored in the Druid, we do some forms of time-based aggregations in Druid.
Yeah, just to add a little bit more on the aggregations, the last couple of slides I talked about the aggregation across our topology hierarchy. We are doing it pre-ingested, but the aggregations across the attribute keys, we are doing it at the query time within Druid, and all the time aggregations we are doing using leveraging Druid to do that. And also to add a bit on the compaction, apart from the secondary partitioning, compaction happening at the secondary partitioning, the way we are ingesting data into Druid is also in a smart way. Then we are based on the entity type, we are sharding the data to the Kafka partitions, so that within a single segment files, the dimensions, the cardinality of the dimensions, some of the dimensions remains low, so that gives us a bit better compression and value. And also query type performance, because the queries are also based on the entity type that we are going to use to query.
Thanks a lot, guys. And the thing about joins is actually one of the most frequently asked question for us. And I think even though Druid supports the lookup and the kind of factor dimension joins, we never almost like recommend anybody to do it, just because from a mathematical standpoint, it just takes more time. And Banu, I think to your point, like there are engines that may advertise and say like, oh, we do joins and we're still really fast, but what they mean by fast is kind of in the 5 to 20-second range, right? To support join, and at the same time, still within sub-second, I feel like it's almost a mathematically impossible problem right now. Maybe 20 years from now, like there's a mathematical, advancement. Someone created a new algorithm, maybe. But like right now, if I look at the market, I mean, if any technology, not just Druid, but any technology, just as a database, if they need to support joins, it's just a lot of heavy lifting they'll need to do, right?
Right.
I think from that perspective, Druid took a very opinionated approach in terms of the recommendation.
Agreed. And also like joins, if you could cache one form of data in memory, then there could be some optimizations and re-optimizations you could do. But the general joins where your data resides in disk, it's really a hard problem because it may lead into a Cartesian product and not really suitable to give a subsequent data.
Yeah, well, speaking of product, I think when Spark first came out, like people can actually do a Cartesian product by doing like a really crazy join. And I think in a later version of Spark, they like by default just disable it, but then return an error message and say like, sure you want to do this because this will be really slow. And I mean that's already like Spark, which supposedly can handle tons and tons of data. Because it's more like ETL, right? It's not so much like ad hoc. But even so, it still, takes so much time to process the data the moment that logic goes in. So I think that's a very interesting point as well. Cool, awesome. Looks like we don't have any other questions. So with that, we'd like to thank you both so much for sharing your experience. And we'll conclude this session now.